You are sitting in a room that seems familiar. The walls, the furniture, the soft weight of your body pressing into a chair, all convey stability. Time flows in its usual rhythm, seconds passing with a quiet predictability. You can reach for objects, observe the light through a window, trace the pattern of shadows on the floor. You assume that space beyond your room is similarly structured. Vast, yes, but filled with stars, galaxies, and matter distributed in ways that can be measured and understood. Yet the deeper we measure, the more the universe seems to contradict this assumption. Vast volumes of space contain almost nothing. Not empty in the casual sense, but profoundly, disturbingly empty. Not merely sparse, but lacking the structures that, according to our best models, should exist. Galaxies, gas, dark matter, they are not spread evenly. They cluster in patterns that defy simple expectations, and the gaps between them are enormous, silent, and resistant to any explanation grounded in the ordinary logic of mass and gravity. These voids are not anomalies in data. They are confirmed repeatedly across observations, across methods, across the decades. Yet their existence raises a question that has no straightforward answer. Why is space far emptier than it should be? And what does that emptiness imply about the universe and about the limits of what you can ever know about it? The illusion of continuity. You expect matter to be continuous, a subtle background that fills space like a fog. Yet when astronomers map the universe on the largest scales, what appears continuous at first glance reveals enormous, empty regions where galaxies are almost entirely absent. Continuity is an assumption, but observation suggests something more fragmented, more deliberate. When we look at the night sky, the stars appear scattered, dense enough that their distribution seems uniform. From this familiar vantage point, it is natural to extend the intuition outward. That matter, while perhaps uneven in small pockets, is fundamentally present everywhere. Yet, the reality of cosmic mapping, conducted over decades with increasingly precise telescopes and surveys, tells a different story. Surveys such as the Sloan Digital Sky Survey or the 2DF Galaxy Redshift Survey do not merely trace galaxies, they trace the spaces between them. And it is in these spaces that continuity breaks down. The largest voids stretch hundreds of millions of light years, nearly devoid of luminous matter. Galaxies are confined to thin filaments, forming a web-like structure, while immense volumes between the filaments are almost entirely empty. These voids are not anomalies that can be dismissed as statistical outliers. They are vast, coherent, and repeated throughout the universe. In effect, the assumption that matter should form a near-continuous background is systematically violated. The universe is not a foggy expanse sprinkled with stars. It is a scaffold of structure suspended above vast, yawning emptiness. The mechanism behind this fragmentation is partially understood through the interplay of gravity and the expansion of space. Regions with slightly higher density in the early universe attracted more matter, growing into clusters and filaments, while underdense regions were left behind, increasingly emptied as the universe expanded. But the magnitude of these voids exceeds what simple models would predict. Even taking into account the gravitational collapse and the influence of dark matter, voids appear too large, too uniform in their emptiness. They are persistent structures, present not for millions, but for billions of years. Observing these gaps forces a re-evaluation of assumptions about uniformity and randomness. In a universe dominated by chance fluctuations in density, occasional voids are expected, but the frequency and scale of observed emptiness do not align with these expectations. The voids appear as if space itself is organized to preserve absence. Even more subtly, the galaxies near the edges of voids tend to be smaller, simpler, and less active than those embedded in denser regions. As if the emptiness influences the development of matter itself, space is not merely a stage on which matter acts, it is a participant, shaping the evolution of what it contains by what it does not. The illusion of continuity also extends to our perception of motion and interaction. Light traveling through these voids is not entirely unaffected. Photons experience slight lensing and redshift anomalies as they traverse the underdense regions, a measurable distortion caused not by additional matter, but by the geometry imposed by absence. Even emptiness has an effect. The gaps bend not just light, but the framework through which we understand the distribution of energy and matter. In this context, the very concept of a continuous universe becomes tenuous. The assumption that space is a neutral background, passively filled with stars and gas, fails under close observation. Continuity exists in perception, not in measurement. Reality, as mapped by decades of astronomical data, is a patchwork of presence and absence, where emptiness is as tangible and influential as matter itself. The unsettling implication is not that the universe is empty, but that it is deliberately structured in its emptiness. This structure is measurable, reproducible, and persistent, appearing across independent surveys and methods. What we assumed was the subtle, uniform haze of matter is instead a complex architecture of voids and filaments. You are not surrounded by a smooth, continuous universe. You inhabit one defined by the stark contrast between what exists and what is missing. Cosmic voids are vast. You might imagine empty space as sparse, punctuated by stars and clusters. In reality, voids stretch hundreds of millions of light-years across, dwarfing the galaxies that edge them. These regions are not incidental. Their scale is comparable to the structures themselves, forcing a reconsideration of how matter distributes in the cosmos. When you look at a galaxy cluster, it seems immense and dense. Yet when mapped on cosmological scales, these clusters are tiny islands, suspended in a sea of nothing. The voids between them are not just empty relative to the clusters, they are overwhelmingly dominant. Surveys reveal that up to 80% of the volume of the observable universe consists of these underdense regions, yet they contain only a fraction of the matter. The sheer magnitude of emptiness is difficult to grasp. A single void can span a distance equivalent to 1 billion Milky Ways, placed edge to edge, stretching uninterrupted in 3 dimensions. The size of these voids is not a minor curiosity. It is a fundamental feature of the cosmic web. Filaments and walls of galaxies thread through the universe, but they do so across voids that define the geometry of everything around them. The structures we can see are confined to a delicate network, while the majority of space is silent, empty, and largely invisible. This reveals a new hierarchy. Voids are as structurally important as the filaments themselves, framing the universe not by presence, but by absence. Observational methods reinforce this reality. Redshift surveys allow astronomers to determine the positions of galaxies in 3 dimensions, uncovering immense regions where few or no galaxies exist. Gravitational lensing, which can reveal hidden mass, confirms that even dark matter, the scaffolding for galaxy formation, is underrepresented in these areas. Cosmic voids are not simply gaps between clusters. They are genuinely underdense volumes that dominate the universe by scale and influence. The persistence of these voids is another striking feature. They have existed for billions of years, surviving the gravitational tug of surrounding matter. While galaxies and clusters merge, collapse, and evolve, voids maintain their emptiness. Expansion of the universe amplifies this effect. As space stretches, the underdense regions grow disproportionately, leaving the surrounding filaments increasingly isolated. In this sense, voids are not static absences. They are dynamic, expanding regions, shaping the evolution of the structures that border them. This vastness also produces subtle, measurable effects on light and observation. Photons traversing these regions experience a slight but observable change in energy, a consequence of traveling through underdense space. The cosmic microwave background shows faint distortions when viewed through the largest voids. The emptiness is not inert. It has an observable imprint on the universe, influencing measurements of expansion, density, and cosmic geometry. Light, like matter, responds to the architecture of absence. The implications extend to our assumptions about scale and randomness. On smaller scales, gaps between stars or galaxies can be dismissed as natural variation. But when emptiness dominates volumes hundreds of millions of light-years across, it ceases to be trivial. Random fluctuations cannot account for these vast voids. Their existence suggests that large-scale structure formation is governed by principles that are subtle, perhaps even counterintuitive. Emptiness is an organizing feature, not a byproduct of chance. In this context, you begin to see that space is not merely vast, it is selectively vast. The universe is defined as much by what is missing as by what is present. Galaxies, clusters, and superclusters exist within a lattice imposed by these voids. The emptiness shapes gravitational flows, constrains cosmic evolution, and subtly bends our measurements of time, distance, and energy. In every direction you look, the voids assert themselves not through motion or light, but through the quiet, uncompromising absence of matter. The vastness of voids also forces a conceptual shift. If the universe's structure is dominated by emptiness, then continuity, uniformity, and homogeneity are illusions when viewed at the largest scales. Space is less a continuous expanse filled with matter and more a patchwork of regions, alternating between concentration and absence. Observing the universe becomes an exercise in measuring absence as much as presence, acknowledging that the voids are not passive background, but central to the architecture of reality itself. The expected density models predict a certain density of matter throughout the universe, yet measurements of galaxy surveys show average densities lower than expected. The missing matter is not a small discrepancy. It is an order of magnitude absence, a silence in the data that speaks louder than the structures we can see. You might assume that the universe, on average, should be filled with matter at a roughly predictable rate. Early cosmological models, grounded in the equations of general relativity and supplemented by observations of the cosmic microwave background, provide a framework for how mass should be distributed. Matter should cluster in predictable ways, with underdense regions balanced by overdense regions, producing a mean density consistent with both theory and observation. Yet when astronomers map galaxies and infer the presence of dark matter, a significant fraction of expected mass is missing. The discrepancy is not subtle. Measurements indicate that voids occupy a far greater fraction of cosmic volume than the models anticipate. Galaxies are concentrated along filaments and walls, yet these filaments contain less matter overall than predicted. The average density of the universe, when considered across sufficiently large scales, is lower than theory demands. This is not a small error bar or a limitation of instruments. It is a persistent, reproducible mismatch. The silence in the data is a statement. the universe is emptier than the mathematics allow. The origin of this discrepancy is rooted in the interplay between ordinary matter, dark matter, and the expansion of space. Dark matter, though invisible, is thought to dominate gravitational scaffolding. It should draw baryonic matter into a web that fills space more evenly. Instead, voids remain pronounced, and even the dark matter density in these regions is lower than simulations predict. Observations from weak gravitational lensing, which measure mass independent of luminosity, confirm that these underdense regions are genuinely lacking in both visible and invisible matter. The implications extend to our understanding of structure formation. If voids are larger and emptier than predicted, the processes that lead to galaxy clustering are incomplete in the models. Inflationary fluctuations, gravitational collapse, and cosmic expansion all interact, yet the result is a universe where large-scale emptiness is more dominant than expected. The universe is not simply a place of scattered islands of matter. It is a network framed and constrained by the voids themselves. Even local measurements echo the anomaly. Galaxies near voids often evolve differently from those in denser regions. Star formation is slower, interactions are rarer, and morphological complexity is reduced. The absence of matter is not passive. It directly shapes the behavior and development of structures that do exist. Density is not merely a statistical property. It has causal consequences, influencing how matter behaves across cosmic time. The discrepancy also challenges assumptions about homogeneity. Cosmology often relies on the principle that, at large scales, the universe averages out to a predictable uniformity. Yet the observed density distribution defies this assumption. Over volumes of hundreds of millions of light-years, the average matter density is lower than predicted, suggesting that even when viewed broadly, the universe is not the smooth continuum once imagined. Continuity is an illusion, replaced by a structured emptiness that dictates where matter can exist and where it cannot. Furthermore, the missing matter carries observational consequences beyond galaxy counts. The propagation of light, the dynamics of cosmic expansion, and measurements of gravitational potentials all respond to the actual distribution of mass. Underestimating the scale of emptiness leads to small but measurable distortions in inferred parameters. The universe, in this sense, communicates the discrepancy through its behavior. Expansion, lensing, and clustering all record the absence as if space itself is signaling a limitation of expectation. Ultimately, the low average density forces a confrontation with the nature of cosmic reality. The universe is not simply sparse, it is selectively sparse. Matter is concentrated, structured, and limited, while emptiness occupies far more volume than any naive prediction would allow. This absence is not chaotic. It is coherent, persistent, and measurable. The silence in the data is not a void to ignore. It is a principle, a defining characteristic of the universe you inhabit, shaping every observation, every calculation, and every assumption about how space should behave. Patterns of absence. Even in emptiness, there is form. Galaxies cluster along filaments, leaving vast voids in between. These patterns are not random. They emerge from processes we partially understand, yet the exact arrangement remains a precise contradiction to the simplest predictions of a uniform cosmos. When you observe a galaxy map, the clustering appears immediately striking. Galaxies are not scattered haphazardly. They collect in long, thin filaments that intersect at nodes, forming clusters and superclusters. Between these filaments lie voids so extensive that they dwarf the structures themselves. This cosmic web creates a rhythm of presence and absence, a pattern where empty space is just as defining as matter itself. At first glance, one might assume this structure is a natural outcome of gravity acting on initial density fluctuations, yet the regularity and scale of the patterns challenge this simplicity. The formation of these filaments is driven by gravity, but not in isolation. Small variations in the early universe, tiny ripples in density imprinted on the cosmic microwave background, amplified over billions of years. Regions slightly denser than average attracted more matter, while underdense regions lost material, deepening the emptiness of the voids. This explains the broad structure, yet the precise arrangement of filaments, their lengths, orientations, and the coherence of their gaps exceed the expectations of the simplest statistical models. Emptiness, in this sense, is not a byproduct. It is a carefully defined framework for matter to occupy. The voids themselves are revealing. They are not uniform bubbles. They have shapes, orientations, and boundaries. Galaxies at the edges of voids tend to line up along the surfaces, tracing the contours of absence. Even within the voids, the rare galaxies that exist are isolated, smaller, and less complex, hinting that the surrounding emptiness influences their formation and evolution. The pattern of absence is an active constraint, shaping the development of the matter that surrounds it. Observation across multiple wavelengths confirms this structure. Optical surveys reveal the filamentary arrangement of luminous galaxies, while radio and X-ray mapping trace the sparse gas and dark matter that support the web. Gravitational lensing measurements show the mass distribution mirrors the visible pattern, even in areas almost entirely empty. The voids are real, the filaments are real, and the pattern is measurable, reproducible, and persistent across the observable universe. This is not an optical illusion. It is the architecture of space itself. The scale of these patterns is unsettling. Individual filaments stretch hundreds of millions of light years, while the voids they surround can span 1 billion light years. You inhabit a universe where the familiar perception of continuity is replaced by a lattice of presence and absence. Light traveling across the cosmos passes predominantly through emptiness, punctuated intermittently by matter, tracing a journey defined more by what is missing than what is present. These patterns influence not just location, but also dynamics. The gravitational pull of filaments shapes the motion of galaxies, directing flows of matter around the voids, channeling the evolution of clusters along the paths dictated by absence. The implication is profound. The large-scale universe is organized not by chance, but by a precise interplay of matter and nothingness. Random fluctuations cannot account for the coherence of the voids or the consistency of the filaments. The cosmic web implies that emptiness is a principle of structure as fundamental as gravity itself. In this sense, the universe is as much about where matter is forbidden to exist as it is about where it collects. Recognizing these patterns forces a reevaluation of how we think about space. You are surrounded by a universe that is not uniform, not continuous, and not neutral. Its emptiness is structured, deliberate, and influential, guiding the evolution of galaxies and shaping the very geometry of observation. The cosmos communicates its logic through the spaces between stars, revealing an architecture defined as much by absence as by presence. In every direction, the patterns of absence are measurable, persistent, and unavoidable. A quiet, inescapable framework that underlies the universe you inhabit. 5. Dark matter's hidden hand. Gravity guides matter, but most of it is invisible. Dark matter forms scaffolding for galaxies, yet the emptiness between filaments is surprisingly stark, as if this scaffolding ends abruptly rather than fading gradually. Observations confirm the voids, even when the hidden mass should fill them. The presence of dark matter is inferred through its gravitational effects. Galaxies rotate too quickly for their visible matter alone to account for their motion. Clusters of galaxies exhibit gravitational lensing that reveals far more mass than can be seen in stars or gas. From these measurements, it becomes clear that ordinary matter, the kind that emits light, is only a fraction of the total mass of the universe. The majority exists in a form that interacts through gravity, but not through light, sound, or any force we can directly detect. Given this invisible scaffolding, one might expect that the structures of the universe would gradually fade into emptiness. The gravitational pull of dark matter should attract baryonic matter, creating a continuum where mass, visible or hidden, extends throughout space. Instead, surveys show a sharp contrast. Filaments are dense, but the voids are nearly pristine. Dark matter itself is underrepresented in these vast regions. Weak lensing maps, which trace mass independent of light, reveal that voids contain far less mass than the surrounding filaments. The emptiness is real, persistent, and not simply a visual illusion. This pattern suggests a paradox. Dark matter is thought to form the framework on which galaxies develop, yet this framework does not extend evenly through space. Filaments trace dark matter's presence, but beyond the edges, the scaffolding abruptly thins. The voids are not merely gaps between structures. They are underdense regions in both ordinary and dark matter, as if the universe imposes limits on where matter may exist. The hidden hand that should guide continuity instead permits discontinuity. The implications are measurable. Gravitational effects in and around voids differ from predictions based on uniform dark matter distribution. Light traveling through a void experiences slightly weaker lensing than it would if the region contained the expected mass. Galaxy motions near void boundaries reveal subtle gravitational asymmetries, indicating that the distribution of matter, visible and invisible, is sharply structured. The emptiness of the voids is encoded not just in what we see, but in how mass behaves where it is absent. The persistence of these voids over cosmic time further emphasizes the anomaly. Filaments grow, clusters merge, and galaxies evolve, yet the underdense regions remain stable. Dark matter, though invisible, follows the same gravitational rules as ordinary matter. Yet the gravitational collapse that shapes the web of filaments does not fill the voids. Even billions of years of interaction cannot erase the absence. Space is structured by both presence and absence, with dark matter defining the boundaries as much as it constructs the scaffolding itself. The scale and sharpness of these voids challenge theoretical models. Simulations of structure formation using dark matter reproduce filaments and clusters, but systematically underestimate the size and emptiness of the largest voids. The models predict a smoother transition from dense to underdense regions, yet observations show abrupt boundaries and expansive voids. This discrepancy is not minor. It implies that our understanding of how dark matter organizes the cosmos is incomplete. The hidden hand is influential, but not all-powerful. It allows emptiness to persist as a dominant feature of cosmic architecture. Even the galaxies that exist near void edges are shaped by this structure. They tend to be smaller, less complex, and less interactive than those in denser regions, suggesting that the influence of dark matter is not simply a question of attraction, but of spatial context. Where the hidden scaffolding is sparse, evolution slows, and complexity diminishes. The voids are defined not just by what they lack, but by how that absence governs everything around them. In this sense, dark matter is both presence and absence. It is a hidden hand shaping the universe, but it is also selective, failing to smooth out emptiness, leaving vast regions nearly devoid of mass. Emptiness is not a passive backdrop. It is an active consequence of the very forces we thought would fill space. The universe, as revealed through observation, is organized not only by what exists, but also by what refuses to exist. The cosmic microwave background, the faint glow of the early universe appears uniform across the sky. Tiny fluctuations seeded galaxies, yet the scale of emptiness today is far larger than these early ripples would suggest. The voids seem to amplify a silence that began nearly 14 billion years ago. The cosmic microwave background, or CMB, is the oldest light observable in the universe. It originates from a time roughly 380,000 years after the Big Bang, when matter and radiation decoupled. At that moment, the universe became transparent, and the photons we now detect were set free, traveling nearly unimpeded across space for billions of years. When you measure the CMB, it appears astonishingly uniform, varying only in tiny fractions of a percent. These minuscule differences correspond to slight variations in density, the seeds of all future structure. From these fluctuations, astronomers have been able to model the formation of galaxies, clusters, and filaments. The physics is well understood. Denser regions attract more matter, growing over time, while underdense regions remain less populated. Yet when we compare the predicted distribution of matter from these initial conditions to the actual universe, a striking contradiction emerges. The vast voids we observe today are far larger and emptier than the original CMB ripples would suggest. The silence of empty space appears to have been amplified over cosmic time in ways that challenge simple extrapolation. This amplification of emptiness implies that the universe is highly sensitive to initial conditions. Small fluctuations in density grew over billions of years into the intricate web of filaments and voids we observe today. Yet the extreme scale of some voids and the sharp boundaries that separate them from matter-dense regions are difficult to reconcile with standard models of gravitational growth. The contrast between what existed in the CMB and what exists now is a reminder that the universe evolves not just through accumulation of matter, but also through the persistent expansion of nothingness. The CMB also reveals anisotropies, slight directional differences in temperature, that correspond to these primordial fluctuations. Observations from satellites like COBE, WMAP, and Planck show that these anisotropies are consistent and measurable. The same physics that produces these subtle temperature differences is responsible for the distribution of galaxies. Yet the vast emptiness of cosmic voids suggests a dissonance between the small-scale ripples of the early universe and the large-scale structures of today. The emptiness is not merely a void in matter. It is a reflection of processes that began nearly 14 billion years ago and persisted uninterrupted across cosmic time. Even the geometry of voids is subtly encoded in the CMB. The integrated Sachs-Wolf effect, for instance, measures how light from the CMB is slightly redshifted or blue-shifted as it passes through regions of varying gravitational potential. Photons that traverse large voids lose a small amount of energy, a measurable distortion that confirms the void's underdensity. Light itself, traveling across billions of years, carries the signature of absence, recording emptiness as a physical effect. This relationship between early fluctuations and current voids challenges assumptions about uniformity. You might assume that the universe averages out over vast scales, smoothing irregularities, yet the largest voids contradict this expectation. Their scale and coherence suggest that emptiness is a persistent principle, not a secondary feature. The silence amplified from the earliest moments of the universe persists today, dominating more space than the galaxies it surrounds. Ultimately, the CMB is both a record and a paradox. It records the initial conditions of the cosmos with extraordinary precision. And yet, those conditions alone cannot fully account for the magnitude of emptiness now observed. The voids are echoes of a primordial silence, expanded, structured, and enduring. Observing the CMB is observing not just the birth of galaxies, but the amplification of absence itself. Space, in its earliest form, hinted at the emptiness that would come to define it, revealing that from the very beginning, absence was as integral to the universe as presence. The limits of observation. You assume you can measure everything if you have the right telescope. But voids stretch beyond the reach of detailed observation. Even where surveys extend, subtle biases arise. The more you look, the more it seems that emptiness is structured, deliberate, and unyielding. Telescopes allow us to map galaxies, clusters, and filaments across vast distances, yet they cannot observe the entirety of the universe at once. Observations are limited by the field of view, sensitivity, and wavelength. Some regions are obscured by dust, gas, or foreground galaxies. Others lie at distances where the faintest galaxies are undetectable. Even the most extensive surveys, such as the Sloan Digital Sky Survey, cover only fractions of the sky, leaving gaps that must be extrapolated. These limitations mean that we are always inferring large-scale structure from incomplete information. Yet the evidence for emptiness persists despite these constraints. Biases in observation are subtle but significant. Bright galaxies are easier to detect than faint ones, making denser regions appear more prominent and underdense regions seem emptier. Similarly, surveys often prioritize certain distances or redshifts, producing uneven sampling across cosmic volume. Sophisticated statistical methods attempt to correct for these biases, yet the results consistently show enormous voids with sharply defined boundaries. The emptiness is not an artifact of measurement, it is resilient under scrutiny and independent of survey strategy. Even as telescopes improve, the challenge remains. Mapping faint galaxies or dark matter within voids requires extraordinary sensitivity and time. Observations using gravitational lensing, for example, can reveal dark matter in principle, but the signals are weak and often swamped by noise. The larger the void, the sparser the matter, and the weaker the signal. Each increment in observational depth reinforces a disquieting realization. The voids are not filled with hidden structure waiting to be discovered. They are genuinely underdense, measurable as empty both in visible galaxies and in inferred mass. This limitation is not merely practical, it is conceptual. You assume that absence might be a temporary limitation, an artifact of incomplete detection, yet every independent method corroborates the emptiness. Voids manifest in optical surveys, radio observations, X-ray mapping, and gravitational lensing alike. Each method, despite different sensitivities and biases, confirms the same reality: that large volumes of space are remarkably devoid of matter. The more you measure, the more persistent the emptiness appears. The structure of emptiness itself becomes increasingly apparent as surveys extend. Voids are not amorphous or diffuse. Their boundaries are coherent, stretching across hundreds of millions of light years. Galaxies at the edges are often aligned along surfaces, tracing the contours of absence. The internal dynamics of voids reveal subtle influences. Matter flows around them. The expansion of space dominates within them, and even light traveling through them experiences measurable effects. Emptiness is not inert. It imposes order and shape, a framework that is detectable even where matter is nearly absent. Limits in observation also imply limits in understanding. You can describe what exists, but the most significant feature of the universe, the vast emptiness, is defined by what is not there. Measurement alone cannot fully capture absence because absence is inherently defined relative to expectation. The larger the void, the more it defies intuition, and the more it challenges the assumption that space is a uniform backdrop. Each survey, no matter how deep or extensive, confronts this fundamental constraint. Emptiness dominates, and our ability to probe it is finite. Ultimately, the limits of observation reinforce a subtle unease. Voids are measurable and persistent, yet they stretch beyond what can be fully surveyed. They are structured, coherent, and resistant to intervention by measurement. Every observation, every survey, every method of inference confirms the same paradox. The universe is not simply populated by matter, but organized around emptiness. Even with perfect instruments, there are regions that cannot be fully known, and in those regions, the universe asserts the quiet, undeniable presence of absence. Gravity's paradox. Gravity attracts, gathering matter into clusters, yet the largest voids resist collapse. Their underdensity is not a temporary fluctuation. It is persistent, stable across billions of years. Observation confirms what theory struggles to accommodate. Gravity is the fundamental force that organizes matter on cosmic scales. Denser regions draw in surrounding material, forming galaxies, clusters, and filaments. This process, repeated over billions of years, creates the large-scale structure of the universe. In theory, even underdense regions should eventually acquire matter through gravitational pull from surrounding filaments. Yet when astronomers map the largest voids, they find them remarkably resilient. Despite billions of years of gravitational influence, these voids remain underdense, their emptiness maintained across cosmic time. The persistence of these voids presents a paradox. Gravity, acting uniformly across space, should gradually smooth out variations in density. Fluctuations, particularly extreme underdensities, are expected to diminish over time. Yet the observations tell a different story. Voids maintain their size and structure, even as surrounding filaments grow denser. The contrast between voids and clusters is not diminishing, it is enduring. Space itself seems to enforce a principle of separation, allowing gravity to operate within filaments while leaving emptiness largely untouched. The dynamics within and around voids highlight this tension. Galaxies near the edges of voids move in predictable ways, influenced by the gravitational pull of nearby filaments, yet these flows do not fill the voids. Dark matter, which dominates the mass of the universe and guides ordinary matter, is also underrepresented within these regions. Even the invisible scaffolding that should encourage collapse is insufficient to overcome the emptiness. The void's resilience suggests that gravitational attraction, though universal, interacts with large-scale cosmic expansion and initial density conditions in ways that limit its ability to homogenize space. Cosmic expansion compounds the paradox. The universe is not static. Space itself stretches over time. In voids, where local gravitational pull is weak, expansion dominates. The result is a natural amplification of emptiness. Regions that begin slightly underdense are stretched faster than surrounding areas, deepening the void and reinforcing its stability. Gravity, which works to gather matter, is countered by the expansion of space itself. In this way, voids are not failures of gravity. They are a predictable outcome of the interplay between attractive forces and the underlying dynamics of the universe. Yet even in simulations, the largest voids appear emptier than models predict, revealing a subtle mismatch between theory and observation. The paradox is further illuminated by scale. Small underdensities eventually smooth out under gravity, while intermediate voids partially fill in. But at the largest scales, the contrast between matter-rich filaments and underdense regions persists. Gravity cannot reach across hundreds of millions of light-years to homogenize the universe. The largest voids exist in a regime where expansion and initial conditions dominate over local attraction, creating a structure that is both persistent and paradoxical. Observational evidence reinforces this. Galaxy surveys, weak lensing measurements, and cosmic microwave background studies all indicate that voids remain coherent over vast distances. The underdensity is measurable in both visible and dark matter. Even as galaxies evolve and clusters merge, the voids maintain their identity. Emptiness is structured, resilient, and fundamental, a persistent feature that defies the intuitive expectation that gravity alone should smooth the universe into continuity. Ultimately, gravity's paradox reveals a disquieting truth about the cosmos. Forces that gather matter and create structure are constrained by the presence of emptiness. The universe is not merely a collection of masses interacting. It is a network of presence and absence where gravitational collapse is selective, filaments grow denser, and voids endure. You inhabit a universe in which the organizing principle of gravity coexists with the persistent dominance of emptiness, a quiet tension that shapes every observation and every calculation across cosmic time. The role of expansion. Space itself is stretching. Galaxies recede from one another at predictable rates, but in voids, this expansion dominates, leaving regions almost entirely devoid of matter. The emptiness is not just absence, it is a product of the universe's own expansion. The universe has been expanding since the Big Bang, a continuous stretching of space that carries galaxies apart. This expansion is measurable through redshift, the systematic lengthening of light waves from distant objects. Galaxies in denser regions resist this expansion partially through their mutual gravitational pull, forming clusters, filaments, and superclusters. In the sparsest regions, however, gravitational influence is minimal. The expansion of space proceeds largely unchecked, widening the emptiness and reinforcing the boundaries of voids. In this context, emptiness is not a passive backdrop. It is a dynamic consequence of cosmic evolution. The voids we observe today were initially only slightly underdense compared to surrounding regions. Over billions of years, the stretching of space amplified these small deficits. As expansion accelerates, underdense regions grow faster than the denser filaments, enhancing the contrast between presence and absence. In effect, the universe is self-organizing its emptiness, not merely distributing matter unevenly, but actively enlarging the voids. Observational evidence supports this dynamic. Voids are not merely low-density regions. They expand at rates slightly faster than the cosmic average. Studies of galaxy motions and redshifts within voids show that local expansion exceeds that in surrounding filaments. This is a measurable, physical effect, not a consequence of perspective. Light traveling through these voids carries the imprint of expansion, revealing the accelerated stretching of the space it traverses. The emptiness is defined not only by what is missing, but by the motion of space itself. The dominance of expansion in voids also constrains structure formation. Galaxies within or near underdense regions evolve differently from those in filaments. Star formation is slower, mergers are rare, and large-scale structures are underdeveloped. Expansion prevents matter from accumulating, reinforcing the void's underdensity over time. What begins as a slight scarcity becomes amplified into vast emptiness, maintained not despite forces, but because of them. Space stretches, and the stretching itself creates and preserves the voids. This dynamic has subtle but significant implications for observation. Measuring the density of the universe requires accounting for how expansion shapes the distribution of matter. The largest voids, stretching hundreds of millions of light years, are effectively regions where space outpaces gravitational collapse. Predictive models must consider not just matter interactions, but the accelerating influence of expansion. The emptiness is not an incidental feature of the universe. It is a predictable, measurable outcome of the cosmic metric itself. Even the largest scale surveys confirm this phenomenon. Observations of filaments, clusters, and voids show a consistent pattern. Expansion dominates where matter is sparse, and gravitational attraction dominates where matter is concentrated. The interplay between these forces produces the stark lattice of the cosmic web, a structure defined equally by filaments and voids. The universe is not uniform. It is stratified, with expansion shaping the boundaries of emptiness as decisively as gravity shapes the boundaries of clusters. Ultimately, the role of expansion reframes the concept of absence. Emptiness is not simply a lack of galaxies, stars, or dark matter. It is an active, evolving product of the universe's own growth. Space itself stretches voids into coherence, amplifying underdensity over billions of years, and producing regions where matter is naturally sparse. The universe is not merely full of things. It is full of intentional absence, sculpted by the expansion of the fabric of reality itself. You inhabit a cosmos where emptiness is as much a consequence of physical law as presence, a structural feature written into the metric of space itself. Voids and light. You expect light to travel uniformly. Yet when photons pass through vast voids, subtle distortions arise. Cosmic microwave background measurements and lensing surveys reveal that emptiness bends reality itself, not by addition, but by subtraction. Light, in the simplest view, moves in straight lines across space. When it passes near a mass, it curves, revealing the presence of gravity. This lensing effect is often used to map both visible and dark matter. Yet even in regions where mass is minimal, light does not traverse space without consequence. In the largest voids, the absence of matter itself produces measurable effects, subtly altering the energy and trajectory of photons. Emptiness, in this sense, is not neutral. It actively shapes observation. One example is the integrated Sachs-Wolf effect, observed in the cosmic microwave background. Photons passing through underdense regions experience a slight energy shift due to the combination of expansion and gravitational potential. As light enters a void, it gains energy falling into the shallow gravitational well, only to lose slightly less energy as it exits, leaving a net measurable effect. The voids, by lacking matter, distort the energy of light in a way that would not occur if the universe were uniform. Absence becomes a physical agent. Weak gravitational lensing provides additional evidence. Light from distant galaxies bends not only around massive clusters, but also across the large-scale network of filaments and voids. Observations show that voids produce negative lensing. The apparent shapes of background galaxies are subtly stretched away from the center of emptiness. These distortions are small, but systematic, measurable across surveys covering millions of galaxies. The effect is not caused by additional mass or energy, but by the stark absence of it. Photons respond to the emptiness as if it were a negative presence, bending reality around nothingness. The impact of voids on light extends across cosmic time. Photons that began their journey nearly 14 billion years ago carry with them the imprint of voids they traversed, encoded as slight redshifts, distortions, or anisotropies. Light acts as a messenger, not just of what exists, but of what is missing. In the vast expanses between filaments, photons reveal the universe's structure through the geometry of absence, demonstrating that emptiness is both persistent and influential. Even familiar astronomical measurements are affected. Distances inferred from supernovae, galaxy distributions, and cosmic expansion can be subtly biased if the influence of voids is ignored. The empty regions modify apparent positions, velocities, and energies in ways that are systematic and measurable. The light we rely upon to reconstruct the universe is not simply tracing matter. It is tracing a landscape defined as much by nothing as by presence. This influence is counterintuitive. We tend to think of space as a neutral stage where objects act and light travels freely. Yet voids show that absence has agency. Their presence dictates the flow of photons, subtly bending them, stretching them, and recording their passage. Light is forced to reveal not only the existence of galaxies and clusters, but also the boundaries and scale of emptiness itself. The cumulative effect is profound. The largest voids dominate cosmic volumes, meaning that much of the light reaching our telescopes has traversed regions of emptiness for millions or billions of light years. The distortions they produce are small individually, but aggregated across cosmic distances, they are significant. The universe is not a simple sum of matter acting through gravity. It is a network where absence, stretched by expansion and defined by underdensity, has measurable physical consequences. Ultimately, the interaction of light and voids reinforces a fundamental realization. The universe is structured not only by what is present, but by what is missing. Emptiness bends reality, amplifies contrast, and communicates structure through the motion of photons. Every observation, every measurement carries the subtle imprint of the voids, reminding you that absence is as influential as presence, and that the cosmos is defined as much by emptiness as by matter. The hierarchy of structure. Clusters, filaments, superclusters, voids. The universe arranges itself in layers of scale, yet the largest structures and the voids that separate them challenge the simplicity of hierarchical models. Observed voids are larger, emptier, and more defined than theory predicts. The universe exhibits a clear layering of structure. Individual galaxies form clusters. Clusters connect along filaments, which themselves intersect at nodes to form superclusters. Beyond this, the vast expanses of underdense space, voids, stretch between these dense regions. This hierarchical framework is supported by both observation and simulation, offering a seemingly intuitive explanation. Small structures form first, merging into progressively larger configurations. Yet when the largest scales are examined, the picture becomes more complex. Observational surveys reveal that the largest voids extend hundreds of millions of light years across, dwarfing even the largest superclusters. These voids are not amorphous or patchy. They have defined boundaries, sharp transitions from near-empty interiors to dense filaments. The scale and coherence of these voids exceed what hierarchical models predict, which assume a smoother gradation of density. At the largest scales, the contrast between matter-rich filaments and vast empty regions is stronger than simulations of structure formation suggest. Even within the filaments, complexity grows with scale. Clusters are not isolated. They exist within interconnected networks that trace the underlying distribution of dark matter. Superclusters appear to form along preferred orientations, extending in coherent patterns over immense distances. Yet despite this connectedness, the voids that separate them are dominant in volume, shaping the geometry of the entire observable universe. The hierarchy is not simply additive. The layers of structure are defined as much by absence as by presence. The persistence of voids across these scales is also striking. Smaller underdensities may eventually collapse under gravitational attraction, but the largest voids maintain their identity over billions of years. Their boundaries, defined by the surrounding filaments, remain sharp. Light passing through these regions experiences subtle but measurable effects, reinforcing the void's role as an active component of cosmic structure. The largest structures are not just collections of galaxies. They exist in a lattice defined by the spaces between them. Dark matter contributes to this hierarchical framework in unexpected ways. Simulations show that dark matter filaments trace the largest structures, yet the voids remain underdense even in this hidden scaffolding. The emptiness between filaments is not smoothed out by the presence of invisible mass. It persists, amplifying the contrast between dense nodes and vast emptiness. The hierarchical model does not fully explain why the largest voids are both so coherent and so persistent. Absence becomes as structurally significant as accumulation. The hierarchy also influences dynamics. Galaxies move along filaments, pulled toward clusters, and accelerated by the gravitational potential of superclusters. Yet the voids constrain these motions. Expansion dominates within underdense regions, stretching space faster than gravitational attraction can compensate. The largest structures, and the spaces that separate them, cannot be understood without considering both the accumulation of matter and the active influence of emptiness. Ultimately, the hierarchy of structure reveals a universe organized by dual principles: presence and absence, density and emptiness. The smallest scales are dominated by gravitational interactions, but the largest scales are dominated by voids and the expansion of space. Observed structures are more extreme, more sharply defined, and more persistent than simple hierarchical models suggest. Emptiness is not a passive byproduct. It is a principal layer in the architecture of reality, shaping everything that exists around it. The universe, at its largest scales, is therefore neither continuous nor uniform. Its hierarchy is a lattice of contrasts, where the emptiest regions define the geometry of the most massive ones. Voids dominate by volume, filaments connect by necessity, and clusters and superclusters exist within this framework of absence. To understand the hierarchy of structure is to recognize that emptiness is not secondary. It is central, persistent, and measurable, a defining element in the organization of the cosmos. The problem of probability. Random distributions should produce occasional large gaps, but not at the frequency and scale we observe. Emptiness seems statistically anomalous, as if some mechanism intentionally organizes the absence of matter. When we model the universe as a random distribution of matter based on initial density fluctuations observed in the cosmic microwave background, we expect that underdense regions will occur. Small voids are a natural consequence of random chance. Slight variations in initial density lead to pockets where less matter accumulates. Over cosmic time, these underdensities grow, but their size and frequency should follow well-defined statistical rules. Large, coherent voids should be rare, yet observations contradict this expectation. Surveys reveal not isolated pockets of emptiness, but extensive regions, hundreds of millions of light-years across, appearing at a rate far higher than probability alone would predict. The cosmic web is dominated by voids, suggesting that randomness is insufficient to explain their distribution. The occurrence of emptiness is structured, repeating, and measurable. The universe appears to organize its gaps with a precision that exceeds what would arise from chance. The problem deepens when considering the boundaries of voids. Random distributions would produce gradual transitions between underdense and overdense regions. Instead, we observe sharp edges, coherent surfaces where the density jumps abruptly from near zero to fully clustered filaments. These boundaries persist across billions of light years, maintaining their sharpness even as galaxies evolve and clusters merge. Probability predicts fuzziness. The universe displays precision. Dark matter, which should smooth out distributions by providing a gravitational scaffold, even in underdense regions, does not erase these anomalies. Weak lensing measurements confirm that the largest voids are underdense in both visible and invisible matter. The gaps are not temporary fluctuations. They are persistent, coherent, and defy the statistical expectations of hierarchical structure formation. Absence is a measurable property, one that the models struggle to reproduce. Even the motions of galaxies reinforce the anomaly. Galaxies near void edges move predictably along filaments, yet there is no evidence that matter from the voids flows inward over time in a way that would reduce their size. Expansion dominates, further amplifying the emptiness. Random chance might produce temporary voids, but the largest voids are too extensive, too persistent, and too sharply bounded to be attributed solely to stochastic processes. This statistical tension has implications beyond the voids themselves. If the largest gaps cannot be explained probabilistically, then the underlying assumptions about uniformity and randomness in the cosmos must be reevaluated. The universe is not merely a random arrangement of matter and energy. It is structured around absence, organized at scales and frequencies that defy simple expectation. Probability alone cannot account for the dominance of emptiness. Observationally, this problem emerges in multiple data sets. Optical surveys, radio observations, X-ray mapping, and gravitational lensing independently confirm the frequency and scale of voids. The same anomaly appears whether measuring visible galaxies or dark matter. The universe consistently produces emptiness at scales far exceeding what chance predicts. It is not a quirk of instrumentation or sampling. It is a fundamental feature of cosmic architecture. Ultimately, the problem of probability reveals a universe that resists simple statistical description. Emptiness is pervasive, coherent, and structured. It occupies more volume than randomness allows and maintains sharp boundaries that defy expectation. You are observing a cosmos where absence is measurable, predictable in ways that presence is not, and dominant in both scale and influence. Probability, in this context, is not a sufficient guide. The universe's gaps suggest an underlying logic, one that organizes emptiness with a precision that challenges assumptions about randomness and uniformity. The coldness of space temperature measurements in voids show near-perfect uniformity. No shock waves, no turbulence, no heat sources. The coldness is a physical manifestation of emptiness, amplifying the sense that these regions are fundamentally distinct from the matter-filled cosmos. Space is not empty in an absolute sense. Even the voids contain trace gas, low-density plasma, and dark matter. Yet when measured, the thermal energy within these regions is strikingly low. The intergalactic medium in filaments and clusters is heated by gravitational collapse, supernovae, and active galactic nuclei. Shock waves propagate through gas-rich regions, producing turbulence and variations in temperature. By contrast, voids are free from these processes. The gas they contain is diffuse and uniform, with temperatures often just a few degrees above absolute zero, approaching the cosmic microwave background itself. The uniform coldness is not merely incidental. It is a consequence of the underdensity that defines voids. With minimal matter, there are fewer gravitational interactions, fewer collisions between particles, and almost no astrophysical processes to inject energy. Expansion dominates, stretching the space and lowering the density further, which in turn suppresses thermalization. The result is a region where matter and energy exist in a state of near-perfect stasis, a contrast to the chaotic energy of filaments and clusters. Observationally, the coldness is measurable. X-ray and ultraviolet surveys reveal almost no emission from these regions, confirming the absence of hot gas or turbulence. Absorption line studies of background quasars show extremely low column densities of ionized hydrogen. Even the sparse dark matter that permeates the voids contributes little to heating, as its influence is primarily gravitational rather than thermal. Emptiness is not just a lack of galaxies. It is an environment where energy itself is minimized, a physical manifestation of absence. This thermal uniformity also reinforces the structural integrity of voids. Hotter, turbulent regions can drive matter outward, mix density gradients, and gradually fill underdense areas. In voids, this mechanism is largely absent. The coldness preserves underdensity, amplifying the contrast between emptiness and the surrounding filaments. Over billions of years, the voids maintain coherence not only in spatial distribution, but in energy, temperature, and dynamical stability. Emptiness is therefore multidimensional, manifesting in matter, expansion, and thermal energy simultaneously. The coldness has subtle consequences for observation. Light traveling through these regions is minimally scattered, producing clearer paths for distant photons. The uniform temperature also reduces distortions in the cosmic microwave background caused by hot gas and filaments. This makes voids detectable not only by what they lack in matter, but by what they lack in energy. Their emptiness is encoded across multiple measurable quantities. Even the rare galaxies that do exist within voids are affected by the cold environment. Star formation is slow, galactic evolution is minimal, and large-scale interactions are rare. The low energy content of the surrounding space constrains the potential for complexity, meaning that even the presence of matter cannot erase the imprint of absence. Coldness is not simply a passive condition, it is an organizing principle that preserves emptiness and shapes the evolution of the sparse structures within it. Ultimately, the coldness of space reveals the distinct nature of voids. They are not merely gaps in the cosmic web. They are environments with measurable, persistent properties. The absence of heat, turbulence, and energy distinguishes them from the matter-filled universe, reinforcing the sense that emptiness is both real and structurally significant. Space in these regions is not neutral. It is cold, quiet, and defined by what is missing. Observing these conditions forces recognition that the universe is composed not just of matter, but of the persistent, measurable absence of it. A silence as profound as any structure is dense. Unexpected isolation. Galaxies near void centers are isolated, small, and simple. They lack the interactions common in denser regions. Observations suggest that voids are not merely gaps, but self-contained environments governed by rules that differ subtly from the rest of space. In filaments and clusters, galaxies frequently interact, merge, and evolve through gravitational encounters. These interactions trigger star formation, distort galactic shapes, and produce a wide variety of structures. By contrast, galaxies located near the center of voids show a strikingly different behavior. They are smaller, more regular in shape, and exhibit slower evolutionary rates. Without neighboring galaxies to perturb them, they evolve in relative isolation, their development dominated by internal processes rather than external influences. The isolation is measurable in multiple ways. Surveys of void galaxies reveal lower stellar masses and fewer spiral arms compared to comparable galaxies in dense environments. Star formation rates are reduced, and supermassive black holes, when present, are smaller and less active. Void galaxies often retain their primordial gas longer, as the lack of interactions prevents stripping or heating. In essence, the internal physics of these galaxies dominates their evolution, unaltered by the external dynamics that shape galaxies elsewhere. Void galaxies also illustrate the influence of large-scale structure on local environments. The gravitational pull within voids is weaker, the density of dark matter is lower, and expansion dominates local dynamics. These conditions limit accretion of matter from surrounding regions. Even small filaments that penetrate a void do not supply significant material. Galaxies within voids are, in a sense, trapped in environments that are both empty and isolated, where the absence of surrounding matter defines their growth and evolution. Observational evidence supports this view. High-resolution imaging and spectroscopy confirm that void galaxies have simpler morphologies and more uniform chemical compositions. Interactions, mergers, and tidal distortions are rare. These galaxies evolve on longer timescales and display a level of stability rarely seen in denser regions. The isolation imposed by emptiness creates a distinct ecosystem within the universe, one governed by absence rather than presence. The implications extend beyond individual galaxies. Void environments influence the surrounding intergalactic medium, which remains diffuse, cold, and largely unaffected by energetic processes common in clusters. Without shocks, turbulence, or high-energy feedback, matter in voids retains a more uniform distribution. Expansion dominates, further amplifying the isolation. The largest voids, spanning hundreds of millions of light years, create conditions in which galaxies exist almost as islands, unconnected to the networks of matter elsewhere. Even the interactions that do occur are governed by unusual rules. Rare mergers in voids proceed slowly, unperturbed by surrounding gravitational structures. Star formation is primarily regulated by internal dynamics rather than external accretion. Dark matter halos exist, but their influence is weaker, allowing galaxies to remain simple and isolated. In this sense, voids are not empty in the conventional sense. They are distinct environments where the usual rules of cosmic interaction are subdued, replaced by conditions that amplify absence and preserve simplicity. Ultimately, the isolation of void galaxies reinforces a broader understanding of emptiness. Voids are not merely passive gaps between structures. They are active environments, shaping evolution through scarcity, expansion, and weak gravitational influence. Presence and absence coexist, but in voids, absence dominates. Galaxies become reflections of the emptiness around them, small, isolated, and undisturbed. Observing these conditions challenges the assumption that the universe is uniform and continuous. Instead, it becomes apparent that emptiness creates its own physics, where isolation is a defining principle, and the absence of matter fundamentally shapes what does exist. The void's age light from the edge of a void has traveled billions of years. Observing it is observing history. Yet these regions appear underdeveloped compared to their surroundings, as if evolution itself is slower or inhibited where emptiness dominates. When we look at the far reaches of a void, we are seeing galaxies and structures as they existed billions of years ago. Photons leaving the edges of these regions have traversed vast distances, carrying information about the past. The images captured by our telescopes are, in effect, historical records, revealing the state of matter and energy across cosmic time. What is striking is the relative simplicity of these regions, even at late cosmic times. Galaxies remain small and isolated, and the large-scale environment shows minimal structural evolution. This underdevelopment contrasts sharply with regions of higher density. In clusters and filaments, galaxies undergo rapid evolution. Frequent mergers, intense star formation, and complex interactions shape their morphology and dynamics. Supermassive black holes grow, gas is heated and redistributed, and feedback processes regulate the evolution of both galaxies and intergalactic medium. Within voids, these processes are absent or greatly suppressed. Evolution proceeds at a slower pace, as if the scarcity of matter and energy delays the unfolding of cosmic history. The persistence of underdeveloped structures in voids is measurable. Surveys comparing galaxies across environments show consistent differences. Stellar populations are older and less varied, gas content remains higher, and internal dynamics are dominated by slow internal processes. Even after billions of years, void galaxies retain characteristics more typical of earlier cosmic epochs. Expansion further isolates them, stretching the space around them and limiting the inflow of matter that could accelerate evolution. Time progresses, yet these regions appear to lag behind the denser cosmos in structural and dynamical complexity. Dark matter contributes to this temporal paradox. While it provides a gravitational framework for structure formation, the lower density of dark matter in voids limits its influence. Filaments grow where dark matter is abundant, but void interiors remain relatively unaffected. Gravitational collapse is slower, mergers are rare, and the amplification of initial fluctuations proceeds at a reduced rate. The very scaffolding that accelerates evolution elsewhere is insufficient to overcome the dominance of emptiness in these regions. Even light itself carries evidence of slowed evolution. Observations of red-shifted galaxies in voids reveal that star formation rates are lower, chemical enrichment is minimal, and galactic growth is limited. Void galaxies preserve simpler morphologies, a record of cosmic youth despite the universe's age. The history encoded in the light shows that emptiness not only defines spatial structure, but imposes temporal constraints, shaping the pace of cosmic development. This phenomenon suggests that voids are more than gaps. They are environments with distinct temporal dynamics. Expansion, underdensity, and isolation combine to create regions where evolution is inhibited, where processes that shape galaxies elsewhere are muted. The large-scale geometry of voids ensures that these conditions persist over billions of years, reinforcing their distinctiveness. Observing these regions is not merely a study of spatial structure, it is a study of cosmic time itself, revealing that absence can slow the progression of evolution across vast distances. Ultimately, the void's age underscores the paradox of emptiness. Light from billions of years ago reveals regions that remain underdeveloped, structurally simple, and isolated. Time has passed, yet evolution has been constrained, as if the universe treats emptiness differently from matter-rich regions. The voids preserve a record of the cosmos that is both ancient and stagnant, a stark contrast to the dynamic, evolving clusters and filaments elsewhere. In this way, emptiness shapes not only space, but the passage of time, maintaining its dominance over both the structure and history of the universe. Cosmic acceleration amplifies emptiness. The universe's expansion accelerates. This acceleration stretches voids disproportionately, making them emptier over time. Observations suggest that emptiness is not static. It grows, emphasizing what is missing as much as what exists. The discovery of cosmic acceleration revealed that space itself is expanding at an increasing rate, driven by what is often termed dark energy. This effect is uniform across the cosmos, but its consequences are most striking in underdense regions. Within filaments and clusters, gravity partially counteracts expansion, limiting the separation of matter. In voids, however, the lack of significant mass allows acceleration to dominate. As a result, voids expand faster than the surrounding universe, stretching their boundaries and deepening their underdensity. The amplification of emptiness is measurable. Surveys of large-scale structures show that the largest voids have grown over time, both in volume and contrast. Filaments and clusters are increasingly isolated by the expanding gaps, while the interiors of voids become more uniform and diffuse. The cosmic web is not simply static, it is dynamically reshaped, with the most empty regions growing disproportionately relative to matter-rich areas. Expansion magnifies absence rather than merely separating matter. This phenomenon also affects the evolution of structures near voids. Galaxies at void edges experience weaker gravitational pull toward the underdense interior, which alters their motion and the dynamics of surrounding filaments. The accelerated stretching of voids contributes to the isolation of galaxies, reinforcing the slow evolution and simplicity observed within these regions. Expansion is not neutral. It actively structures the universe by amplifying the spaces between structures, not just the structures themselves. The impact of acceleration is reinforced by dark energy's persistent influence. Unlike gravity, which depends on local density, dark energy acts uniformly, affecting every cubic meter of space. In regions of high density, its effect is partially masked by gravitational attraction. In voids, where gravity is minimal, acceleration operates unopposed. This leads to the counterintuitive conclusion that emptiness itself experiences a force, growing and stretching more rapidly than regions containing matter. Absence becomes an active component of cosmic dynamics. Observational consequences extend beyond the spatial distribution of matter. Light traveling through expanding voids experiences slight alterations due to the changing gravitational potential, contributing to anisotropies in the cosmic microwave background and measurable lensing effects. The expansion of emptiness leaves its imprint not just on the geometry of space, but on the propagation of energy across it. Void growth is encoded in the very photons we observe, revealing that absence shapes perception as much as presence. The growth of emptiness also influences future cosmic evolution. As voids stretch and deepen, filaments become increasingly isolated. Clusters remain bound, but the network connecting them weakens, producing a universe in which matter-rich regions are islands within an ever-expanding sea of emptiness. The acceleration does not simply separate objects. It redefines the cosmic architecture, making absence a more dominant feature over time. The universe is not only sparsely populated, it is becoming sparser, with emptiness amplified by fundamental physics. Ultimately, cosmic acceleration forces a redefinition of what it means for space to be empty. Voids are not static voids. They are dynamic, growing, and increasingly isolated. Their expansion accentuates the contrast between matter and emptiness, reshaping the observable universe in ways that cannot be ignored. You observe a cosmos where absence is not merely a background condition, but an evolving, measurable entity whose growth is as significant as the formation of galaxies and clusters. The universe, in this sense, is defined not only by what exists, but by the active expansion of what does not. The challenge to simulations. Computer models predict the formation of voids, yet the largest, emptiest voids are systematically underrepresented. Simulation fails not in detail, but in principle. The observed universe is emptier than the mathematics allows. Modern cosmological simulations are built on the laws of physics as we understand them. Gravity, dark matter, hydrodynamics, and the initial conditions derived from the cosmic microwave background. These models reproduce the large-scale web of filaments, clusters, and voids with remarkable fidelity. Small-scale structures emerge naturally, and intermediate underdensities appear with the expected frequency and distribution. Yet when the largest voids are compared to these predictions, a mismatch becomes apparent. Observed voids are larger, emptier, and more sharply defined than any simulation predicts. This discrepancy is not minor. Simulations produce underdense regions, but they tend to be partially filled with matter and less coherent than what surveys reveal. Galaxies in simulated voids are more numerous, and dark matter is distributed more smoothly. In reality, the largest voids exhibit underdensities approaching 90 to 95%, with galaxies and dark matter almost entirely absent. The contrast between dense filaments and empty interiors is far more pronounced than models anticipate. The failure is fundamental, reflecting limits in our understanding of cosmic structure. Simulations assume that matter behaves according to known physics, that initial fluctuations evolve under gravity and expansion, and that the statistical rules governing density variations are sufficient. The largest voids suggest otherwise. Absence is amplified, persistent, and structured beyond what these principles predict. Emptiness is not merely a consequence of insufficient mass, it is an organizing feature, one that simulations cannot replicate at the largest scales. This limitation also has observational consequences. Surveys map filaments and clusters accurately, and simulations reproduce these structures well. The predictive failure occurs in the vast expanses between them. When comparing simulated light propagation to observations, subtle effects of voids, gravitational lensing, the integrated Sachs-Wolf effect, and redshift distortions are underestimated. Photons traveling through actual voids encounter less matter and shallower gravitational wells than the simulations allow. The discrepancies are cumulative, measurable, and systematic. The challenge extends to cosmic evolution. Simulations suggest that underdense regions should gradually fill in over billions of years as matter is drawn inward by surrounding filaments. In reality, the largest voids resist collapse, maintaining underdensity over time. Expansion dominates over gravity within these regions, and the expected smoothing of density contrasts does not occur. The result is a universe where emptiness persists at scales and intensities that the models cannot reproduce. Attempts to adjust simulations by tweaking initial conditions or increasing resolution fail to resolve the discrepancy. Even when statistical extremes are considered, the largest voids remain rarer in models than in reality. This indicates that the problem is not computational, but conceptual. The equations governing structure formation are correct in isolation, yet they cannot account for the observed dominance of emptiness. The voids are too large, too empty, and too sharply defined to arise from standard hierarchical growth alone. Ultimately, the challenge to simulations underscores a disquieting truth. The universe does not conform entirely to expectations based on matter, gravity, and initial fluctuations. It is systematically emptier, suggesting that absence has been organized by principles that are subtle, pervasive, and not fully captured by existing models. Voids are not incidental. They dominate the cosmic landscape in ways that defy predictive mathematics. Observing the universe reveals a level of order in emptiness that models cannot generate, forcing a reconsideration of the assumptions underlying our simulations of reality. The silence of signals. Void regions emit almost no radiation. Surveys across the electromagnetic spectrum detect only a trace. Their silence is a measurable property, reinforcing emptiness not as a conceptual absence, but as an observable physical phenomenon. In the universe, radiation is produced wherever matter interacts, accelerates, or heats. Stars emit across visible and infrared wavelengths. Hot gas shines in X-rays. Cosmic rays, magnetic fields, and active galactic nuclei generate radio waves and gamma rays. Dense regions are bright and noisy. Voids, by contrast, are conspicuously quiet. Their interiors contain neither luminous galaxies nor hot intergalactic gas. The energy density is remarkably low, and photons traversing these regions experience minimal scattering or emission. This silence is not theoretical. Radio surveys show extremely low emission from void interiors, with brightness temperatures far below the cosmic average. X-ray mapping confirms the near absence of hot gas, while ultraviolet absorption lines indicate extremely diffuse hydrogen. Even high-energy instruments detect little activity. Across every measured frequency, the voids register as empty, and the absence of radiation is itself a physical signature of emptiness. The measurable quiet extends beyond local voids to those billions of light-years away. Observations of distant cosmic regions show that even early voids, when the universe was younger and denser overall, were underluminous compared to surrounding filaments. Light from quasars, gamma-ray bursts, and background galaxies passes through these regions without notable interaction, further confirming their low energy content. The emptiness is pervasive, persistent, and consistent across time and space. The silence has structural implications. Radiation in dense regions can drive feedback, heat surrounding gas, and induce star formation. Without radiation, voids remain cold and diffuse. Their interiors are not sites of energetic processes, but reservoirs of inertia where matter evolves slowly and simply. Expansion dominates. Gravitational interactions are minimal, and energy flows that shape structure elsewhere are almost entirely absent. Emptiness becomes an active constraint on physical processes, not merely a lack of matter. This phenomenon also influences observation. Photons traveling through voids retain their original energy more faithfully than those passing through clusters. The absence of scattering and thermal effects makes voids ideal laboratories for measuring cosmic background radiation, yet the very clarity of these measurements underscores the void's emptiness. Light propagates through a landscape defined by what is missing, reinforcing the idea that voids are as much defined by absence as by any local structure. Even the few galaxies that do exist in voids contribute minimally to the radiation budget. They are small, isolated, and underdeveloped, with low star formation rates and minimal energetic output. Their contribution to the void's emission is negligible compared to the surrounding cosmic web. The quietness is therefore both a property of the environment and a product of the diminished activity of its sparse inhabitants. Ultimately, the silence of signals confirms emptiness as a measurable, physical phenomenon. It is not merely an observational convenience or a conceptual gap. Across scales, wavelengths, and epochs, voids manifest absence in detectable ways, producing regions where energy, motion, and light are drastically reduced. Their quiet is not passive. It is a defining characteristic of the cosmos, shaping the behavior of matter, the propagation of light, and the evolution of galaxies. Observing voids is observing a universe defined by what is missing as much as by what exists, a silence that is measurable, persistent, and fundamental to the structure of reality itself. Cosmic topology. The universe has a shape and structure on the largest scales. Emptiness punctuates that topology. Observations imply that voids are integral to the universe's overall geometry, suggesting absence is as fundamental as presence. Topology, in the cosmological sense, refers to the large-scale arrangement and connectivity of space. Galaxies cluster into filaments, filaments intersect at nodes forming superclusters, and voids stretch between them, creating a cosmic web. This web is not a random scattering, but a coherent structure spanning billions of light years, with voids occupying most of the volume. The shape of the universe is therefore defined as much by what is missing as by what is present. Measurements of galaxy distributions and cosmic microwave background fluctuations indicate that voids are not incidental gaps. They follow patterns consistent with the underlying curvature and expansion of space. Large-scale surveys reveal that the spatial arrangement of voids, filaments, and clusters reflects an interconnected lattice, where the emptiest regions help define the geometry and orientation of the densest. The voids are part of the cosmic skeleton, shaping paths of light, the flow of matter, and the evolution of structures across space and time. Void shapes themselves carry topological information. While small voids are approximately spherical, the largest voids are often elongated or irregular, aligning with surrounding filaments and superclusters. Their boundaries are sharp and coherent, and their placement is correlated across enormous distances. This suggests that voids are constrained not only by local density fluctuations, but by global geometric properties of the universe. Emptiness is therefore not merely a byproduct of matter distribution, it is an element of cosmic architecture. Observations of light propagation provide further evidence. Gravitational lensing, the integrated Sachs-Wolf effect, and redshift surveys all indicate that voids influence the geometry of space in measurable ways. Photons traverse underdense regions along paths defined by the arrangement of matter and emptiness, revealing the universe's curvature through subtle shifts in trajectory and energy. The structure of voids, their size, shape, and connectivity, encodes information about space itself, showing that absence is topologically significant. Even the expansion of the universe interacts with topology. Dense filaments resist expansion due to gravity, while voids expand more freely. This differential stretching enhances the contrast between emptiness and structure, reinforcing the lattice-like character of the cosmic web. The universe is not homogeneously stretching. It is a network in which absence amplifies the shape of presence. Voids define distances, orientations, and connections on scales where ordinary matter is sparse, revealing that emptiness actively participates in cosmic geometry. The topological role of voids also affects evolutionary dynamics. Matter moves along filaments toward clusters, but the presence of voids channels this motion, guiding flows on vast scales. galaxies and gas evolve within a lattice constrained by emptiness, meaning that the absence of matter is a boundary condition for the development of structure. In this sense, voids impose a framework that is as essential to cosmic evolution as gravity or dark matter. Ultimately, cosmic topology shows that emptiness is more than a backdrop. Voids are integral to the universe's shape, orientation, and evolution. They influence the motion of matter, the propagation of light, and the curvature of space itself. Observing the universe's large-scale structure is observing a duality. Presence defines the nodes, but absence defines the connections, the distances, and the geometry. Emptiness is not incidental. It is a fundamental, measurable aspect of cosmic architecture, a pervasive feature that shapes the universe as decisively as the densest clusters of matter. 20. The paradox of scale. You can measure clusters accurately, yet voids defy the same precision. The larger the region, the emptier it seems, contradicting the assumption that large-scale averages smooth out irregularities. Scale reveals emptiness as an active principle. In cosmology, there is an expectation that as you examine larger volumes of space, local fluctuations average out. Small overdensities and underdensities might exist, but over hundreds of millions of light-years, the universe should appear roughly uniform. Clusters of galaxies are measurable, their mass, luminosity, and distribution predictable within statistical margins. Yet when voids are considered, this assumption breaks down. The largest regions of space are far emptier than any smoothing principle predicts. Observations confirm that the emptiest voids expand over scales comparable to superclusters themselves. Whereas small voids can be modeled with some accuracy, the largest voids span hundreds of millions of light-years, dwarfing any filament or cluster. The underdensity in these regions is extreme, with matter occupying only a fraction of the space predicted by average cosmic density. The larger the region examined, the more pronounced the absence becomes, revealing that emptiness is not random noise, but a structural principle that dominates at scale. This paradox has implications for measurement. Galaxy surveys are designed to quantify density, velocity flows, and clustering statistics. In dense regions, these measurements are consistent with theoretical expectations. In voids, however, the scarcity of matter introduces uncertainty, not from instrumentation, but from the universe itself. Sampling larger volumes does not reduce variance. It increases contrast. The largest voids consistently show underdensities far below the cosmic mean. Rather than averaging out, emptiness asserts itself, making scale a tool to reveal absence rather than presence. The paradox also manifests in the dynamics of space. Within clusters and filaments, gravitational interactions are dominant, driving complex motions and mergers. Within voids, expansion dominates, pulling matter away from the center and reinforcing underdensity. Over larger scales, the effects of expansion are magnified. The void does not simply grow in size, its relative emptiness intensifies. Scale is not neutral. It interacts with emptiness to create regions that defy statistical expectation and resist standard models of matter distribution. Dark matter, which underlies all large-scale structure, amplifies this paradox. Simulations predict that dark matter should populate voids more evenly than visible matter, creating a partial skeleton, even within underdense regions. Observations, however, show that the largest voids remain largely empty, even in the invisible component. The emptiness becomes more pronounced with scale, suggesting that what is missing is as real and persistent as what is present, reinforcing the idea that absence has its own organizing principles. Even light traveling through these regions reflects the paradox. photons pass through underdense space with minimal interaction, creating measurable effects on background radiation and lensing patterns. The larger the void, the clearer its signature, and the more it emphasizes the contrast between emptiness and the surrounding structure. Scale is not a smoothing device, it is a magnifying lens, highlighting the universe's commitment to absence. Ultimately, the paradox of scale forces a reconsideration of assumptions about the cosmos. Where clusters obey predictable patterns, voids reveal that absence is not incidental. Emptiness becomes dominant, persistent, and measurable precisely at the scales where uniformity was expected. Observing larger regions of space is not observing a homogenized universe. It is observing a cosmos in which emptiness asserts itself as a fundamental principle, shaping geometry, dynamics, and perception. The larger you measure, the more clearly absence defines reality. Implications for matter. The existence of vast empty regions forces reconsideration of matter distribution. It implies that the universe is not merely less dense than expected, it is selectively dense, with absence as much a defining feature as presence. Matter in the universe is not distributed uniformly. Filaments, clusters, and superclusters represent concentrations of mass, yet these are interwoven with voids that dominate the cosmic volume. This selective density challenges the assumption that matter merely spreads evenly over large scales. Instead, the universe appears to organize itself around emptiness, allowing matter to collect in specific locations while leaving enormous gaps elsewhere. Measurements of galaxy density and dark matter distributions reinforce this view. In dense regions, gravitational interactions and accretion proceed as predicted. Matter flows along filaments toward nodes, producing predictable clustering. In voids, however, matter is not simply sparse, it is almost entirely absent. The distribution is bimodal rather than continuous. Dense regions and empty regions coexist, with transitions that are abrupt and coherent over hundreds of millions of light years. The universe is structured not by what it contains, but by the deliberate absence between structures. This selective density has consequences for cosmic dynamics. Gravity pulls matter into overdense regions, yet the persistence of vast voids shows that absence exerts an effective organizing influence. Expansion dominates where matter is scarce, stretching emptiness and preventing gravitational collapse. The voids themselves act as boundaries, constraining the movement of matter and shaping the evolution of filaments and clusters around them. Absence becomes an active factor, defining where matter accumulates and how structures develop over cosmic time. The implications extend to the scale of dark matter. Simulations predict that dark matter should partially fill voids, smoothing density contrasts. Observations, however, indicate that even dark matter underdensities are more pronounced than models allow. The universe is not only selectively dense in visible matter, it is selectively dense in all matter. Absence is measurable, consistent, and fundamental, suggesting that the cosmic architecture is guided by more than the simple attraction of mass. It is guided by the organization of what is missing. Even on the scale of galaxies, selective density plays a role. Galaxies within voids are small, isolated, and evolve slowly. Their growth is constrained not just by the lack of interactions, but by the surrounding emptiness. In dense regions, interactions, mergers, and accretion drive complexity and evolution. In voids, absence dictates simplicity, illustrating that the distribution of matter is inseparable from the distribution of emptiness. Presence is meaningful only in contrast to what is not there. The selective nature of matter also shapes observable phenomena. Light propagates differently through dense filaments and empty voids, affecting lensing, redshift, and cosmic background measurements. Surveys sensitive to both visible and invisible matter reveal that the gaps themselves carry information about the universe's structure and history. Emptiness, in effect, encodes geometry and dynamics just as much as matter does. Ultimately, the existence of vast voids forces a conceptual shift. The universe is not merely a collection of matter sprinkled through space. It is a dual system, defined equally by the distribution of matter and the distribution of absence. Emptiness is not a passive backdrop. It is a defining property that shapes the organization, dynamics, and evolution of all matter. Observing the cosmos in this light reveals a universe where presence is significant only because absence has been organized, persistent, and measured across billions of light years. Matter and emptiness coexist, but emptiness dominates the volume, asserting itself as a principle as fundamental as the mass it separates. The illusion of randomness. You might assume voids are random accidents. Observation suggests otherwise. The alignment of voids, their shapes, and their distribution indicate underlying principles not accounted for in standard models. At first glance, emptiness might appear incidental, a consequence of matter clustering elsewhere. Small voids could be dismissed as statistical fluctuations, natural gaps that emerge where gravity fails to draw sufficient mass. Yet surveys of the cosmic web reveal that voids are far from haphazard. Their positions are correlated across vast distances, their boundaries are sharp, and their shapes often reflect the arrangement of surrounding filaments and superclusters. The largest voids exhibit elongation and orientation that align with the large-scale structure, implying that their formation is constrained by more than local density fluctuations. The coherence of voids is measurable. Statistical analyses of galaxy distributions and dark matter reveal that voids are not isolated features. They form a network that complements the dense structures. Adjacent voids are often connected, creating low-density corridors that define the spacing of filaments. Their placement affects the flow of matter, guiding galaxies along predictable paths and shaping the overall architecture of the universe. This network-like arrangement is inconsistent with purely random distribution. Emptiness is patterned, structured, and integral to cosmic design. Void shapes also defy randomness. Smaller voids approximate spherical regions, as expected from simple expansion models, but the largest voids are highly irregular, flattened or elongated along specific axes. These orientations correlate with surrounding gravitational structures, suggesting that voids are molded by forces beyond immediate density contrasts. The absence of matter is not uniform. It is anisotropic, constrained, and aligned. Random processes cannot reproduce such coherent geometries. Large-scale emptiness reflects a principle that acts across hundreds of millions of light years, shaping absence with as much care as gravity shapes presence. The implications extend to dark matter as well. Simulations incorporating dark matter predict underdense regions, but they fail to reproduce the specific alignments and distributions observed. Observed voids are larger, emptier, and more coherent than models allow. Randomness alone cannot account for this. Instead, the patterns suggest that absence is not an accidental byproduct of structure formation, but a regulated feature of cosmic evolution. Emptiness follows rules, subtle and persistent, that remain largely unexplained. Even the interactions of light with voids reinforce this sense of order. Photons passing through aligned voids experience gravitational redshifts and lensing effects that reflect the void's coherent shapes. The impact of void geometry on background radiation and galaxy observations is measurable, revealing that emptiness organizes space and influences observable phenomena. Random placement would produce a more chaotic, unpredictable set of signals. Instead, absence conveys structure, imprinting itself on the measurements that define our perception of the universe. Void alignment also influences the evolution of matter. Galaxies near void boundaries are funneled along filaments, moving in directions constrained by the void network. The absence of matter within the voids defines the paths and interactions of galaxies, shaping the growth of structures. Emptiness acts as a guiding framework rather than a passive gap. Its patterning determines the dynamics of surrounding matter over billions of years, amplifying the sense that voids are purposeful features rather than accidents. Ultimately, the illusion of randomness dissolves under observation. Voids are not scattered haphazardly. They are organized, aligned, and shaped by principles not captured in standard cosmological models. Emptiness is patterned, persistent, and measurable across scales, influencing the distribution and evolution of matter as decisively as the densest clusters. The universe is defined not only by what exists, but by the careful, structured absence between structures, a silent architecture that is neither random nor incidental, but fundamental to the cosmic order. Observational consistency. Every independent survey confirms emptiness: optical, radio, X-ray, gravitational lensing. Multiple methods converge on the same paradox. Space is emptier than it should be. Everywhere we look. Optical surveys map galaxies directly, revealing the locations of clusters, filaments, and voids. These images show that the largest voids contain few, if any, galaxies. Even faint dwarf galaxies are sparse within the interiors of these regions. Statistical analyses confirm that the observed underdensities are not anomalies or gaps in detection. They are real features of the cosmic web. Radio observations reinforce this conclusion. Neutral hydrogen mapping detects diffuse gas that might populate otherwise empty regions. Within voids, radio surveys detect extremely low levels of HI emission, indicating that even the most tenuous gas is largely absent. This is not a subtle effect. The contrast between dense regions and void interiors is stark, consistent across multiple radio frequencies and instruments. Emptiness is encoded not only in the absence of stars, but in the absence of the raw material from which stars might form. X-ray observations reveal the same pattern. Hot gas trapped in gravitational wells emits X-rays, highlighting clusters and filaments. In voids, X-ray flux is virtually non-existent. There is no hidden reservoir of high-energy material, no diffuse plasma, to compensate for the apparent absence of matter. Across the electromagnetic spectrum, the evidence is consistent. Voids are profoundly underdense. Emptiness is not confined to a single wavelength or observational technique. It is a multimodal feature of the universe. Gravitational lensing provides further confirmation. Light from distant galaxies is subtly distorted by the gravitational influence of intervening matter. Dense regions produce measurable lensing signatures, but voids produce minimal effect. Weak lensing surveys demonstrate that even the invisible component of mass, including dark matter, is far less abundant in void interiors than in surrounding filaments and clusters. Observational consistency across independent methods confirms that voids are genuinely empty, not merely underrepresented in visible matter. The convergence of these methods is remarkable. Optical, radio, X-ray, and gravitational lensing are independent approaches, each subject to its own systematic errors and limitations. Yet all detect the same pattern. The largest regions of space are significantly emptier than expected. This consistency rules out observational bias, instrumentation error, or selection effects as explanations. Voids are real, pervasive, and uniform across cosmic scales. This consistency also extends across cosmic time. Observations of high redshift galaxies indicate that underdense regions existed billions of years ago and have persisted through cosmic evolution. The emptiness is not a transient feature, but a long-lived aspect of the universe. Structures within dense regions evolve rapidly, yet voids maintain their underdensity, suggesting that absence is stable and persistent, reinforcing its role as a fundamental property of cosmic architecture. Even subtle measurements of the cosmic microwave background support the same conclusion. Integrated Sachs-Wolf effects and temperature anisotropies indicate that photons traversing voids experience weaker gravitational potentials, consistent with the observed lack of mass. The emptiness is encoded in the very light that carries information across billions of light years, providing independent confirmation that voids are structurally and dynamically distinct from the rest of the universe. Ultimately, observational consistency leaves little room for doubt. Across wavelengths, techniques, and epochs, the universe exhibits persistent, measurable emptiness. Void regions are not statistical anomalies, instrumental artifacts, or minor deviations from expected density. They are coherent, large-scale features, replicated in every independent survey, revealing that space itself is defined as much by what is absent as by what exists. The more methods we employ, the clearer it becomes. Emptiness is a fundamental, measurable principle of the cosmos, unavoidable and pervasive wherever we look. Emptiness as a boundary. Voids define limits. They separate structures, distort light, influence gravity. In this sense, absence becomes an active agent, shaping the observable universe without ever containing matter itself. When you observe the cosmic web, what immediately strikes you is not only the presence of galaxies and clusters, but the space between them. Filaments stretch across millions of light years, intersecting at nodes where matter accumulates. These filaments are framed and constrained by the surrounding voids. The absence of mass within voids imposes boundaries on the movement of matter, dictating the paths along which galaxies, gas, and dark matter can flow. Emptiness, though lacking substance, acts as a scaffold that defines structure. Light propagating through voids illustrates the same principle. Photons traveling across underdense regions experience reduced gravitational influence compared to paths through dense clusters. The bending of light, the timing of its travel, and the energy it retains are all subtly affected by the empty spaces it traverses. Absence shapes observation. A void does not add mass to deflect light. It subtracts influence, altering trajectories and perceptions. In this sense, emptiness is not neutral. It exerts measurable effects on the universe precisely because it is missing. Gravitational interactions further emphasize voids' boundary-like role. Dense structures attract matter, but the surrounding voids resist collapse due to their underdensity and the accelerating expansion of space. The lack of mass within voids amplifies the gravitational contrast with filaments and clusters, constraining the evolution of structure along specific paths. Galaxies at void edges move along predictable trajectories dictated by the differential between empty and dense regions. Absence delineates the limits of motion and organizes the flow of matter across billions of light years. Void boundaries are also sharp and coherent. Surveys of the cosmic web reveal that transitions from dense filaments to empty interiors are abrupt rather than gradual. The edges of voids are not fuzzy zones of slowly diminishing density. They are well-defined regions where the character of space changes fundamentally. This clarity reinforces the idea that emptiness is a distinct and measurable property of the universe, not simply the result of statistical variation or observational bias. Absence is framed, shaped, and persistent. The influence of voids extends temporally as well. Because light takes billions of years to traverse cosmic distances, observing a void is observing its history. The persistence of underdensity over time indicates that emptiness acts as a boundary, not only spatially, but dynamically. Structures cannot evolve or accumulate in regions defined by absence. The void constrains not just the arrangement of matter, but the history of cosmic evolution, shaping trajectories and interactions across vast scales. Even the largest voids, spanning hundreds of millions of light years, demonstrate the same principles. They isolate clusters, separate filaments, and influence gravitational potentials over extreme distances. Expansion accentuates these effects, stretching the voids and reinforcing their boundary-like character. Far from being passive gaps, voids are active determinants of the cosmic landscape, defining where structures can exist and how light and matter propagate through the universe. Ultimately, emptiness functions as a framework, an invisible architecture that structures space itself. The universe is organized not only by the presence of matter, but by the deliberate absence between structures. Voids separate, delineate, and constrain. They distort observation, channel evolution, and amplify gravitational contrast. Absence, in this sense, is not simply a lack, it is an active property, measurable and persistent, shaping the observable cosmos without ever manifesting as matter. Observing a void is observing the limits of structure, the edges of influence, and the silent geometry imposed by absence across the universe. The unresolved question. All these observations lead to one persistent conflict. Space is far emptier than models predict, and yet it is not uniform emptiness. The paradox is not merely that matter is missing. It is that its absence is structured, measurable, and deeply incompatible with simple expectations. What does it mean to live in a universe where emptiness itself is a defining property? If the universe were truly random, voids would appear as irregular gaps of varying size, shape, and orientation, occurring occasionally as statistical outliers. Dense clusters would be interspersed by underdensities, but extreme emptiness would be rare. Instead, surveys consistently show that voids are extensive, coherent, and patterned. They align over hundreds of millions of light years, their shapes reflecting the arrangement of surrounding filaments and superclusters. Emptiness is not incidental. It exhibits regularity, a structure imposed across scales that should average out in a random distribution. Observational consistency across multiple wavelengths reinforces this conclusion. Optical surveys detect sparse galaxies, radio observations reveal minimal gas, X-ray instruments show almost no hot plasma, and gravitational lensing confirms low dark matter density. Independent measurements converge on the same paradox. Absence is dominant, measurable, and persistent. Random processes alone cannot produce such uniformity in emptiness. Each void is both empty and carefully positioned, a spatial feature that guides matter and light alike. The non-randomness of voids also has dynamic consequences. Expansion stretches empty regions, enhancing underdensity and creating a feedback loop in which absence dictates the evolution of surrounding structures. Galaxies and dark matter flow along filaments into dense nodes, their paths constrained by the neighboring emptiness. The largest voids persist over billions of years, resisting gravitational collapse and maintaining extreme underdensity. Absence shapes not only spatial distribution, but temporal development. The universe is not a chaotic assembly of matter. It is a lattice in which emptiness channels growth and motion. Even light reveals the ordered nature of voids. Photons passing through underdense regions experience gravitational effects distinct from those traveling through filaments or clusters. Integrated Sachs-Wolf signals, lensing distortions, and anisotropies in the cosmic microwave background all reflect the coherent geometry of voids. Absence leaves measurable imprints on the very light that allows us to perceive the universe. Random distributions would blur or obscure these signals. Instead, they reinforce the structured nature of emptiness. The paradox extends to theoretical models. Standard cosmology predicts underdense regions, yet the largest voids are systematically underrepresented in simulations. Adjustments to initial conditions, resolution, or statistical thresholds fail to reproduce the observed coherence, alignment, and emptiness. Models are correct in principle, but incomplete in practice. Reality exhibits a pattern of absence that mathematics alone cannot fully generate. Voids are too vast, too empty, and too structured to arise from randomness alone. Ultimately, the universe demonstrates a duality. Matter defines nodes and filaments, but absence defines volume, boundaries, and paths. Emptiness is not a void in understanding. It is a principle that shapes geometry, dynamics, and observation. To perceive the cosmos is to perceive what is not there as much as what is present. Structure emerges as much from absence as from presence, and randomness cannot explain the regularity of emptiness on the largest scales. Living within such a universe challenges intuition. We experience space as filled with matter, stars, planets, gas clouds. But on the largest scales, the cosmos is overwhelmingly empty, and that emptiness is organized. Presence is defined against absence, activity against silence, mass against void. The universe is a lattice of being and non-being, and what is missing is as essential to reality as what is observed. The emptiness is not a passive void. It is an active framework, pervasive, structured, and inescapable.